Another trend to talk about deals kind of with our ionic radius, so we're forming ions. And we want to talk about how much energy is actually associated with ripping off electrons. So that energy is called the ionization energy, so the energy required to form an ion. And we're going to form our ions one electron at a time. So if we look at calcium, calcium likes to form a 2+ ion. Okay, it's in group 2A, so it's located right here. This is calcium. It likes to form a 2+ ion. So our ionization energy, we're going to look at one ion at a time. So the first ionization energy is the first electron that's ripped off. Okay, so we'd represent that equation like this. And this is called the first ionization energy. The second ionization energy is going to be the second electron that's taken off. So we start with the calcium plus ion, rip off the second electron, and this would be the second ionization energy. So we have values here, the first ionization energy, the second ionization energy, regardless of the element, regardless of what's going on, is always going to be more or require more energy than the first electron is. Okay, and that's because when you remove one electron, you now have less shielding, so greater effective nuclear charge, so it's going to require more energy to rip off that second electron. So our trend for ionization energy is actually going to follow the effective nuclear charge, because the energy that's required to rip off an electron depends on how tightly that electron's being held. So if it has a higher effective nuclear charge, it means that it takes more energy to remove the electron. So as the effective nuclear charge increases, it's going to take more energy to rip off an electron. So for the trend for our first ionization energy, as we go from left to right, effective nuclear charge increases, okay, because we have more protons. So our ionization energy is going to increase as we go across. And our ionization energy increases as we go up. Okay, because our electrons are closer to the nucleus, so they feel a greater pull. Excuse me. Now there are a few exceptions to that. So if we look over, we're just focusing on first ionization energies. That's the most important for us. Okay. Here are our elements, and they're listed in order of their atomic number. Remember, Z represents atomic number, the number of protons. And we'll see that you kind of have these pockets of increasing values. So we have hydrogen to helium increases. Then from lithium to neon increases. That's the N equals 2 or the second period. Then from sodium to argon, we increase. Okay. Now there are a couple exceptions. Beryllium and boron. Okay. Beryllium's here, boron's over there. we would expect that the ionization energy would increase. So we would expect that boron would have a higher energy than beryllium. Also, another thing that we see, nitrogen and oxygen have this same flip-flop. So does magnesium and aluminum, which are located underneath beryllium and boron. So what exactly is going on here? Well, to explain why this flip-flop happens, we have two different locations. We have beryllium and boron, okay, and magnesium and aluminum. They're underneath each other. Okay, so that's one kind of pocket of exception that happens. And then we have this nitrogen versus oxygen flip-flop. Also, we'll see the same flip-flop, phosphorus and sulfur, which are underneath them. So in order to understand this, we actually want to look at the energy or the energy level diagrams. Okay, so those diagrams where we have the up arrow and the down arrow, and when we look at those, we'll actually see why these have a flip-flop of energy. So if we look at beryllium versus boron, as well as magnesium and aluminum also fall into this category since they're underneath beryllium and boron, so they're going to have similar electron energy level diagrams. If we look at, we'll look at beryllium. We have 1s and 2s. And then this is boron. Beryllium has 4 electrons, so we have 1, 2, 3, 4. Boron has 1 more. 1, 2, 3, 4, 5. For the first ionization energy, the electron that's going to be removed is the outermost electron. So for boron, this is the outermost electron. For beryllium, this is the outermost electron. So for beryllium, when we remove an electron, we're removing an electron that's been paired up. Okay? And remember, Hund's rule says that although electrons like to be single, they do like to be paired up. So once we pair it up, it's actually going to take more energy to remove the paired up electron. Whereas even though this electron for boron, outermost electron, is in a higher up energy level, it's by itself. Okay, so it's lonely. It's easy to pick this off versus this one that's already paired up. So whenever something's easy, that's representing less energy to be removed. So our electron that's paired up for beryllium takes more energy to remove than the single electron of boron. So again, this is an exception. Beryllium versus boron and magnesium versus aluminum. They're right underneath. And why this is an exception, if you look at the values, is that we would predict that the ionization of boron would be greater than beryllium because boron is to the right of beryllium. And as we move from left to right, ionization energy should increase. The problem is, in actuality, beryllium has a greater first ionization energy level, and that's because it takes more energy to remove the paired ion of beryllium. Similar concept for nitrogen versus oxygen and phosphorus versus sulfur. Okay, phosphorus and sulfur are underneath nitrogen and oxygen. Okay, oxygen is further to the right of nitrogen, so we would predict that oxygen had a greater first ionization energy than nitrogen, but in actuality it's flip-flopped. And the reason for this again has to do with the pairing of the electrons. So we have 1s, 2s, 2p. This will be, we'll go nitrogen, oxygen. Nitrogen has 7 electrons, oxygen has 8. 1, 2, oh, let's do black. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. And this last electron for oxygen gets paired up. But what happens is, for our nitrogen here, by removing this electron, we're disrupting this full half shell. Now I said that wrong. We're disrupting a half full subshell. Okay, so the 2p is a subshell of the n equals 2 level. And when we half fill this, that is more energetically favorable than a partially full subshell. Okay, so it's going to require more energy to disrupt our half full subshell than it is to pluck off this one. If we pluck off this electron, that leaves us with a half full subshell, and that's actually more energetically favorable than to disrupt that half shell or half full subshell. So it's going to require more energy to remove an electron from a half full subshell. So although electrons like to be paired up, it's more energetically favorable to have every available orbital just have one electron. So those are our 2 exceptions for our first ionization energy.